Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Heat Transfer Combined with Chemical Reactions. Till now we have seen individual momentum transfer problems, we have seen individual heat transfer problems. Today we will see a few heat transfer problems followed by heat transfer combined with chemical reactions. Okay. In today's lecture what we are going to see, we are going to discuss three different problems. All of them are based on a spherical geometry, like even the reaction whatever we are going to take. So, that is also on a spherical catalyst pellet surface. Okay. Spherical catalyst we have, so then there is a reaction is taking place, and then because of that reaction the heat transfer, heat transfer is being affected. Okay. So, then how the temperature distribution is going to change with the heat generation because of the reaction, that is what we are going to see. Since we are taking a spherical geometry, spherical particles we are taking. So, what we do before going into the problem where the reaction is also involved, we take a spherical geometry and then see how the temperature distribution is taking place. Let us say if the same spherical particle is surrounded in an infinite fluid medium, right. The infinite fluid medium is there. So, but that fluid medium is stagnant, that is motionless, and then in that fluid medium there is a heated sphere is there. So, now that heated sphere, from that sphere surface to the surrounding stagnant fluid, the heat transfer is taking place, and then heat transfer is taking place only because of the conduction, because the fluid is stagnant, right. So, then under such conditions we know the correlation for the Nusselt number is Nu is equals to 2. So, that derivation also we see first, and then we go into a porous spherical particle, then we go into a catalytic spherical particle where the reaction is also taking place in a step by step manner. So, heat transfer from a sphere to a stagnant fluid. So, the purpose is to study the heat conduction in fluid surrounding a sphere in absence of convection, because we are taking infinitely bounded stagnant Newtonian fluid. Since it is stagnant, there will not be any convection. So, consider a heated sphere of radius r suspended in a large motionless body of fluid, right. Temperatures at the surface of sphere and far away from the sphere are T r and T infinity respectively. Consider the fluid is incompressible Newtonian liquid, and then assume that thermophysical properties, that is Cp, rho, mu, etc., are independent of the temperature difference. So, they are not being affected by the difference T r minus T infinity, and there is no chemical reaction and gravity is not considered in this problem. Okay. So, schematically if you see what you have, we have a spherical particle, non-porous spherical particle is there, and then it is bounded in infinite amount of fluid, that is there are no wall effects, that is the purpose taking the infinitely bounded large volume of the fluid. Okay. So, this spherical particle is suspended in this large volume of the fluid, right. So, the surface temperature is T r, radius of the sphere is capital R, and then far away temperature is T infinity, right. So, now in this case the T r is higher than the T infinity. So, then heat transfer is taking place, and then surrounding fluid whatever is there. So, heat transfer may be taking place in this manner because of the conduction, right. So, because why conduction only, this fluid is stagnant, motionless. So, stagnant in the sense V is 0. If V is 0, all the convection terms in the left hand side whatever are there in energy equation, they will be negligible. Okay. So, for this case what is the T, right, how it is changing, and then here the conduction would be dominated in the radial direction only, because there is no rotation. So, in theta direction there will not be any transfer of the momentum, or there will not be any transfer of energy in theta direction, because there is no rotation of the sphere, right. And then similarly in pi direction also there is nothing is happening. So, whatever the transfer is there, radially it is transferring to the surrounding fluid. That is the reason temperature is function of R only. What is that function of R? That is what we are going to find out now. Okay. And then once we have the temperature profile, so then you can find out what is the Nusselt number. So, this you might have studied, it is equals to 2. So, that also we do the derivation. So, fluid is stagnant, that is given in the problem statement. So, there is no need to solve the equation of motion, because when we solve the energy equation in the left hand side velocity terms are there. So, then in general before getting into the energy equation we have to get the velocity of the fluid or velocity distribution of the fluid, we must get it. So, however, in this case that is not required, because the fluid is motionless, it is stagnant. So, V is 0. So, then left hand side terms of energy equation we do not need to worry, and in all these problems we are doing for the steady state condition. So, dou T by dou T will also be 0 because of the steady state. Okay. So, the energy equations we need to solve, and then in energy equation also consider only conduction as specified in the problem, because the fluid is stagnant. So, we will be taking only conduction terms. However, we as a normal practice we will be simplifying the energy equation to get that expression for the conduction in the radial direction in spherical coordinates. Okay. So, that way we can do, or you can do what you can do simple heat balance, because of the conduction, then in heat balance, that is heat transfer taking place because of the conduction in r direction. So, that heat balance you can do and then get the required energy equation, required simplified energy equation for the temperature distribution. But we follow our normal convention whatever we have been following in this course, that is we simplify the energy equation. So, energy equation in spherical coordinates is given here. So, steady state problems we are solving. So, this term is 0, fluid is stagnant. So, then all velocity terms should be 0, right, and then conduction is taking place in only in the r direction, and then thus temperature is function of r. So, then this term would be there, right. So, next is temperature is not function of theta, it is not function of phi also, because only conduction in the radial direction, that is what we are taking. So, what we get from here? So, this is the equation. This equation we can integrate to get the required temperature distribution, right. This same equation we may also get in a conventional way of obtaining the governing equations, conservation equation, that you take a spherical particle of radius r, right, and then this particle is suspended in an infinite volume of a stagnant fluid. So, that also geometry also you take r infinity, r is equals to infinity also you can take. So, in general we write r infinity, r is equals to infinity also you can take, that is far away. What does it mean by r is equals to infinity? It is not infinity, but compared to the r infinity value is very large, very large, that you can take infinity. Okay. So, now here the surface temperature is Tr, here the surface temperature is T infinity, right. So, now what you can do, you can take a volume element like in between these two limits like this, right. So, this is the volume element in the spherical geometry. So, whose thickness is dr, So, let us say radius of this element radius of this element is small r, and then radius of outer element is r plus dr. So, that the thickness of this element is dr. So, now what is the rate of heat entering in r direction because of the conduction, minus what is the rate of heat leaving in the r direction at r plus dr because of the conduction, that you can write down, right, and then you take the balance is equals to 0, because we are not taking any accumulation term here, steady state. So, then you get this equation, that way also you can do it. Okay. So, now on integration what we get, r square dou T by dou r is equals to C1. So, the same thing we can write dou T by dou r is equals to C1 by r square. So, this is also going to be useful for our further calculations. So, now once again if you do the integration, what you get? You get T is equals to minus C1 by r plus C2. So, now we need two boundary condition to get these two constants C1, C2. One condition is at r is equals to capital R, T is equals to Tr, at r is equals to infinity, T is equals to T infinity. This is what we know. Okay. So, this is the temperature profile that we got. Now, we will obtain this constant C1, C2. At R is equals to capital R, T is equals to TR. So, minus C1 by R plus C2 is equals to TR. And then at R is equals to infinity, T is equals to T infinity, that is minus C1 divided by infinity, that is 0 plus C2. So, that means C2 is equals to T infinity we get. Now, from this boundary condition, if you substitute C2 is equals to T infinity, minus C1 by R is equals to TR minus C2, that is T infinity. So, C1 would be T infinity minus TR multiplied by R, right. So, now these two constants C1 and C2, if you substitute here, you get the final temperature distribution, like T is equals to minus T infinity minus TR capital R by small r plus T infinity. The same thing we can write T minus T infinity divided by TR minus T infinity is equals to capital R by small r. So, this is the temperature distribution that we get for this case of a heat conduction from a sphere to a stagnant Newtonian fluid. Okay. So, now we try to find out the Nusselt number expression for this case. So, rate of heat transfer at sphere surface due to conduction is nothing but QR at R is equals to minus K dou T by dou R at R is equals to capital R. So, dou T by dou R we have seen is C1 by R square, right, at R is equals to capital R. So, minus K by capital R square, and then C1 is nothing but R multiplied by T infinity minus TR. So, that is K by R TR minus T infinity is nothing but the rate of heat transfer at sphere surface due to the conduction. Similarly, if at all there is some convection, little convection whatever is there, so that rate of heat transfer at sphere surface due to the convection is H TR minus T infinity. H may be very small in this case, so which can be negligible. Okay. So, equating these two modes of heat transfer, that is K by R TR minus T infinity is equals to H TR minus T infinity. So, TR minus T infinity both sides cancel out. So, then we have H R by K is equals to 1. So, both sides if you multiply by 2, then you have H 2 R by K is equals to 2, that is nothing but H d by K is Nusselt number. So, Nusselt number for the case of heat conduction from sphere to Newtonian fluid is 2. This you might have studied in your heat transfer courses, right, you may be remembering. So, this is how we get the derivation for this problem, right. Now, we take next problem, heat conduction in spherical shell. So, now what we have taken till now, we have taken a geometry spherical particle, right, and then from there the surrounding fluid, the heat conduction is taking place. Now, we take a spherical shell, right, and then in that shell, some kind of holes have been made, and then remaining portion of the shell is insulated. Then how to get the temperature profile? So, here also in this case also only heat conduction is taking place, because there is no fluid involvement at all. At least in the previous case there was a fluid, but that was stagnant, but in this problem there is no fluid at all. Okay. So, consider a spherical shell with inner and outer radii R1, R2. Make a hole in the shell at north pole by cutting out conical segment in the region between theta is equals to 0 to theta is equals to theta 1. Pictorially, if you see here, inner radius of the shell is R1, outer radius of shell is R2, right. And now, what we are having here, this solid is insulated surface, whatever the solid surface is this insulated. So, now we have theta is equals to 0 location, this one, and theta is equals to pi location is this one. So, now between theta is equals to 0 to theta is equals to theta 1, what you do, make a hole, that hole should be conical segment like this, right. So, the angle of this conical segment is theta 1, that is what we understand. Now, similarly, make a hole at south pole by cutting out conical segment in the region theta is equals to pi minus theta 1 to pi 1. So, now this location is nothing but theta is equals to pi minus theta 1. So, from theta is equals to pi to theta is equals to pi minus theta 1, whatever the angle it is making, from that angle you make another hole at the south pole like this, right, and then remaining surface is insulated here. The temperature at theta is equals to theta 1 is T1, at theta is equals to pi minus theta 1, temperature is T2, right. Since now this the spherical shell, these holes have been made. So, the remaining portion though is insulated, the heat conduction is taking place, right, and then heat conduction is taking place in the theta direction obviously here. So, that temperature as function of theta direction, that we have to find out now. Okay. What is the temperature profile in the shell? In this case there is no involvement of fluid, hence only conduction is the mode of heat transfer. Conduction would also be there only in theta direction, it will not be there in r and phi direction according to schematic given. And then energy equation in spherical coordinates we have to simplify since steady state. So, this term is 0, there are no velocity terms at all since there is no fluid involvement. So, left hand side all terms are 0. Temperature is function of theta only, it is not function of r and phi. So, these two terms are gone. So, then what we get? We get 1 by sin theta dou by dou theta of sin theta dou t by dou theta is equals to 0, right. So, that means sin theta dou t by dou theta is equals to C1, dou t by dou theta is equals to C1 by sin theta. This further if you integrate, say you get t is equals to C1 ln tan theta by 2 plus C2. But now here the range of theta is between 0 to pi only. So, then whatever the tan values would be there of that per theta region. So, you will be getting only positive values. So, then because of that one you can remove this modulus. So, that is t is equals to C1 ln that is t is equals to C1 ln tan theta by 2 plus C2. Now, this C1, C2 we have to find out using the boundary conditions that we are having. The same temperature expression is written again here. At theta is equals to theta 1, t is equals to T1, that is given. So, T1 is equals to C1 ln tan theta 1 by 2 plus C2, right. At theta is equals to pi minus theta 1, t is equals to T2, that is also given. So, that should be equals to C1 ln tan pi minus theta 1 by 2 plus C2. So, T1 minus T2, that is this equation minus this equation, if you do, you get C1 ln tan theta 1 by 2 minus ln tan pi minus theta 1 by 2, that is C1 ln tan theta 1 by 2 divided by tan pi minus theta 1 by 2 you can get. So, now this expression you can substitute either in this here this equation, or you substitute here in this equation and then you can find out C2, right. Then you will get some kind of expression, because from here you can get, you are getting C1 is equals to T1 minus T2 by ln tan theta 1 by 2 divided by tan pi minus theta 1 by 2. This is what you are getting, but not necessary to do that one again. It becomes lengthier calculations, because in this type of heat conduction problem, the temperature distribution we are getting in the form of a ratio between differences, two temperature differences. This is one temperature difference. Similarly, other temperature difference expression if you get for T minus T2, then you can have a expression T minus T2 divided by T1 minus T2 function of theta, because this T minus T2 will also be having some constant. We will not evaluate and then see how we can get rid of this constant by taking these two ratios. So, this T1 minus T2 is written once again here. Now, similarly, if you wanted to write T minus T2, what you have to do? theta 1 you have to replace by theta, right. T is nothing but temperature at unknown theta. T1 is nothing but temperature at some known theta 1, right. T2 is nothing but temperature at some known pi minus theta 1 angle, fine. So, now similarly if you wanted to know unknown temperature at some unknown theta value, you can write you can replace the theta 1 by theta by writing T minus T2 is equals to C1 ln tan theta by 2 minus ln tan pi minus theta 1 by 2, that is this one, C1 ln tan theta by 2 divided by tan pi minus theta 1 by 2. So, now you can do this divided by this expression. So, then C1 would be cancelled out. So, that will simplify our life, not requiring to calculate this C1 C2 separately. Okay. So, that is T minus T2 by T1 minus T2 if you write, you get ln tan theta by 2 minus ln tan pi minus theta 1 by 2 divided by ln tan theta 1 by 2 minus ln tan pi minus theta 1 by 2. So, this at this unknown theta value, what is unknown temperature, that you can find out using this expression, right. So, now combined heat conduction and reaction energy in spherical catalyst pellets. So, that is the last problem that we are taking in this class. Okay. So, let us see this statement. Consider a spherical catalyst pellet of size R. Thermal conductivity of the pellet is K. Inside the pellet, chemical reaction is occurring due to which the rate of heat generation is Sc. Then heat is lost to outer surface of pellet and then to a gas stream by convective heat transfer. So, that means you have a spherical catalyst pellet, some pores may be connected or broken or whatever. So, like this you have a catalyst particle. So, now inside this one reaction reaction is taking place in this inside this catalyst pellet. So, because of the reaction the heat is being generated and then that is Sc. So, then obviously the temperature distribution would be there here. In this case we will not have isothermal conditions. So, at this surface what is the temperature, we do not know, because now the reaction is taking place inside the catalyst surface. So, then depending on that Sc, whatever heat generation is there. So, this temperature on the surface, let us say you designate is Tr. So, that Tr is not a constant, it is a function of whatever that heat generation because of the chemical reaction. Okay. So, now whatever the heat is there, since the reaction is taking place inside the catalyst porous catalyst pellet, the temperature would be maximum at the center, right. At center we have maximum temperature, okay, because reaction is taking place inside the catalyst pellet. So, now whatever the heat is there, so at the center maximum, that is being transferred towards the outer surfaces, outer layers of the catalyst pellets, right. So, it reaches the surface of the catalyst surface, then it moves to the surrounding gaseous stream because of the convective heat transfer. So, there is a some amount of loss of temperature is there. So, that temperature of gas stream is Tg, that is known. So, because usually these catalytic reactions heterogeneous reactions, and then one of the phase is either gas or liquid in general, mostly gaseous reactions. So, that there is a gas stream flowing around this catalyst surface, so that it is forming a kind of film layer. So, that temperature of that gas stream is Tg, that is known. Okay. So, now gas stream at temperature Tg, that is known. Convective heat transfer coefficient is H, that is also known. Thermal conductivity of the pellet K, that is also known. Assume rate of heat generation is constant throughout, this is very important, right. Develop steady state expression for the temperature profile and obtain expression for the maximum temperature in the system. So, this is what we are going to have. So, now some temperature. Now, here what we understand, the temperature is function of R, that is what only you are taking. So, this you have to find out. Okay. So, the conduction equation you have to use here also, because mostly it is conduction dominated within the, because whatever the changes in the temperature are there within the catalyst pellet are only there, that is what we are taking place. Whatever the Tg temperature is the surrounding gas stream temperature, but that is forming as a film only, very thin film only. Okay. So, assumptions, constraints, steady state problem we are taking, negligible flow inside porous sphere, so that we can take only conduction in general, because inside the porous structure, whatever the catalyst pellet you take, inside the porous structure, in general these reactants, whether the gases or liquid reactants, whatever are there, they move from one location to the other location, primarily because of the diffusion, and then under such conditions the bulk motion is very small, negligible, so that we can take only conduction heat transfer here. So, only conduction mode of heat transfer inside the pellet, conduction is only in the R direction. So, T is function of R, that is what we have to find out, right. Now, energy equation in spherical coordinates is given here, rho Cp dou T by dou T plus Vr dou T by dou R plus V theta by R dou T by dou theta plus V phi divided by R sin theta dou T by dou phi is equals to K multiplied by 1 by R square dou by dou R square dou T by dou R plus 1 by R square sin theta dou by dou theta sin theta dou T by dou theta plus 1 by R square sin square theta dou square T by dou phi square plus Sc. This is nothing but heat generation because of the chemical reaction inside the catalyst pellet. So, steady state, this term is 0, and then there is no fluid movement at all, or conduction only we are taking. So, velocity components are 0. Temperature is function of R only, it is not function of theta or phi. So, these two terms are 0, and then this heat generation because of the chemical reaction should be there. How much it is we do not know, actually it is given, let us assume it is given, okay, but it in general changes during the progress of the reaction, but however in our problem it has been mentioned, it is being maintained throughout the reaction, constant Sc has been maintained throughout the reaction. So, finally we have K by R square dou by dou R square dou T by dou R plus Sc is equals to 0, right. Now, this equation we can rewrite dou by dou R of R square dou T by dou R is equals to minus Sc R square by K. Now, when you integrate, R square dou T by dou R is equals to minus Sc by K R cube by 3 plus C1. Now, you take that R square to the right hand side. So, dou T by dou R is equals to minus Sc by K R by 3 plus C1 by R square. Now, once again if you integrate, T is equals to minus Sc by K R square by 6 minus C1 by R plus C2. So, now you have to find out this C1, C2, right, then only you can find out the temperature. So, it is not straightforward, because only Tg, one temperature is known, right. Boundary conditions you have to apply such a way that its known value is there. If you use certain kind of boundary condition which is again dependent on some other variable or parameter, it is of no use. For example, here Tr is the temperature at the surface, but it is function of this Sc. So, this is not known as of now, this is not known. So, we have to find out, then we can get this constant and then get this final temperature. Directly we cannot assume Tr is constant, though Sc is constant, we do not know what that is Sc, but Tr, once Sc is known, Tr can be found out, what is that constant Tr can be found, okay. So, that first we have to do, okay. So, the same equation is written here again. So, the C must be 0 in this case, because this temperature cannot be infinite for any value of r, and then if you substitute r is equals to 0, that is at the center, this equation is going to produce you infinite value, that is not acceptable. So, C1 must be 0. So, the final simplified temperature is this one, right. So, now this C2 we have to find out, right. So, you may be thinking again here, we have only one Tg value. So, we can find out this C2, that you may be thinking, right. But that is also not possible here. Why it is not possible? Tg is known, but at what R value this Tg is there, that we do not know. Then only we can apply these boundary conditions. In the case of Tr, we know the location at R is equals to capital R, but this Tr is function of Sc. So, then even though location we know, Tr exact value of Tr we do not know a priori. So, we cannot use this boundary condition also. Whereas, the other value of temperature, the other side wise, the reverse way is true. Tg is known, but at what location that Tg is existing, that we do not know. What is the film thickness, that we do not know. Film of gas stream, that is surrounding catalyst pellet, in which the heat loss is taking place because of the convection, the thickness of the film is not known. So, either of the boundary conditions directly we cannot use. So, what we have to do? We have to do a few simplifications now, that we are going to do now. So, heat losses to surroundings would provide required boundary condition to obtain C2. So, what are the heat losses that we have to find out? At the surface of sphere, rate of heat transfer due to conduction and convection must be equal in order to find out the new boundary condition to get this C2. So, we have to find out rate of conduction at the surface as well as the rate of convection at the surface to get a final boundary condition. So, rate of conduction at surface, that is minus k dou T by dou R at R is equals to capital R, should be equals to the rate of convection at the surface is H T R minus T G, right. So, where T R is temperature on surface of spherical catalyst pellet, that is function of Sc, it is not one constant value. Tr is also constant, but it is not a priorily known. Okay. Why Tr is constant? Because Sc is constant throughout the reaction. That way it is constant we know, but what is that constant we do not know. So, then that is the reason we cannot use directly that one as a boundary condition. So, from equation number 3 we are finding out dou T by dou R, because we have to find out minus k dou T by dou R. So, dou T by dou R from equation number 3 is minus Sc by k 2R by 6, and then this dou T by dou R we are finding out at R is equals to capital R, that is at the surface. So, you substitute R is equals to capital R, then you get minus Sc R by 3k. So, now minus k dou T by dou R is equals to H T R minus T G, that is what we know. So, now here in place of dou T by dou R at R is equals to R, we substitute minus Sc R by 3k. So, minus k multiplied by minus Sc R by 3k is equals to H T R minus T G. So, that is we get Sc R divided by 3 is equals to H T R minus T G. Now, from equation number 3, that equation number 3 is T is equals to minus Sc by k R square by 6 plus C2. Now, here what you can do, you need to know this Tr. So, what you do at R is equals to R, T is equals to Tr, you substitute here. So, then you get Tr is equals to minus Sc R square by 6k plus C2, right. So, now this you can use here in this expression, equation number 5. Now, substitute Tr, that is minus Sc R square by 6k plus C2 in equation number 5. Equation number 5 is this one, Sc R by 3 is equals to H Tr minus Tg. So, now in place of Tr we are writing this one. So, now we can write Sc R by 3H is equals to minus SC R square by 6K plus C2 minus TG, that is C2 is equals to SC R square by 6K plus SC R by 3H plus TG, this is what we get. So, this is the C2. C2 is strongly dependent on SC and then TG as well, in addition to H and K values, right. So, now this C2 you can substitute in equation number 3, which is the final temperature distribution. T is equals to minus SC by K R square by 6 plus C2. In place of C2 we can write SC capital R square by 6K plus SC R by 3H plus TG. So, T minus TG is equals to SC R square by 6K multiplied by 1 minus R square by capital R square plus SC R by 3H. This is the final temperature distribution. Right. So, now we have to find out the maximum temperature, which is nothing but at R is equals to 0. So, in this equation if you substitute R is equals to 0, you get T max minus TG is equals to SC capital R square by 6K plus SC capital R by 3H. So, if you take SC capital R square by 6K common, you will get multiplied by 1 plus 2K by HR. This is in the form of reverse of Nusselt number. So, that way if you write, you can write 4K by H2R. So, this is nothing but reverse of the or inverse of the Nusselt number. So, this is the maximum temperature at the center of the catalyst surface. Okay. The references for this lecture are provided here. Primarily all 3 problems you can find out in this book, Bird, Stewart and Lightfoot. Transport Phenomena. In this book, Transport Phenomena by Bird, Stewart and Lightfoot, you can find out all these problems. Thank you.